We have Alex. I'm going to butcher your last name if I don't ask you.
Okay, it's Natale.
Natale. So Alex got his PhD at UC Riverside, and now he's at the Korea Institute for Advanced Studies. He's going to tell us about not so simple models.
Thank you very much. So today I'm going to talk about some work on this. It's in a paper in press, but here's the archive link. So it should appear in January. So instead of the usual dark matter introduction, I'll sort of use this analogy of the allegory of the cave from Plato's Republic. So in this analogy, there's some people, and they're forced to live in this cave. And all they can see of the outside world, or what they think is the world around them, are these shadows on this cave. And there's some light source, like some fire or something, that's causing the shadows. And the shadows are from these objects that are, they're built to represent, real world objects, like a horse or this vase. And these people are walking between the fire, and that's what's producing the shadows. So all they have to sort of develop their worldview of the world outside their own experience are these shadows and these sounds. So I think, wrong way. So I think this is sort of a good analogy for a situation with dark matter, because we can see the effects of dark matter, but this is through the gravitational effects or cosmological, like the CMB, but we can't measure it directly. So we don't really have any idea what the ultraviolet physics looks like, or what the dark sector is. Like it could be made out of some sort of composite objects or something like that. So I just like to say we're sort of in the situation with dark matter where we're in the cave. We know that something exists. We can see these gravitational effects. But we have no idea what dark matter is made of, what interactions it can have. We know what it can't have by looking for it and failing to find it. And then we don't even know if we can directly detect dark matter or produce it at colliders. And we also don't really have any real concrete idea if it has connections to other unsolved problems in physics. So this is sort of the framework for what I'll be talking about today. So as a particle physicist, though, there's, so in my talk today, I'll talk about dark matter and neutrino mass as experimental motivations for beyond the experimental physics. I'll talk about this idea in keeping with this Plato theme called Plato's fire, where you have these non-abelian discrete symmetries, and I'll talk about how they've been used previously to discuss neutrino oscillation. And then I'll talk about my model, which is this, I call the binary tetrahedral scotogenic model, where I use a particular non-abelian discrete symmetry to try and predict a realistic neutrino mixing matrix, and see if I can make a non-trivial quark mixing matrix, and what the consequences are for this for dark matter in particular. So I'll start with dark matter and neutrino mass. So as a particle physicist, there's basically three major approaches to dark matter that we're all familiar with. There's an effective field theory approach, where I have a non-renormalizable theory that uses higher dimensional operators to parameterize my dark matter standard model interaction. This is nice. You have only two parameters. You have the scale of your new physics and some Lorentz structure, and then the mass of your dark matter. Of course, there's also like simplified models. Someone recently asked me, simplified from what? And the name is really coming from the idea that from Susie. But broadly, it just means any sort of simple model where you have just a mediator and like a dark matter standard model interaction. So you have three parameters. So you have some coupling constant between your dark matter and the mediator. You have the mass of the mediator now, and then you have mass of your dark matter. And of course, you can have more complicated models like the MSSM or any sort of supersymmetric model. And these can have as many parameters as you want. So there's a few pitfalls to the simplest approaches, which are most appealing. For instance, the effective field theory can break down at colliders. Not only if the energy sort of goes, if the scale of your new physics and the energy of your collision are sort of comparable, and in most field theories, your predictions can break down. But there are some other effects with mono W boson signals at the LHC, where people pointed out effective field theories have been problematic. You can also use the simplified models, particularly the Z prime. People have seen that if you choose naive couplings for your new gauge boson, it can also break down. But the important part, I think, for the Z prime is if you add a dark Higgs, which is necessary to give mass to this Z prime, at least in a straightforward way, it actually significantly alters your dark matter phenomenology. So in terms of dark matter, if you have a more realistic model of a massive Z prime, you have to have this dark Higgs, and it actually makes your dark matter have some interesting effects. There's some also running effects and the effects of multimodal mediators that make this more simplified approach to be a little more complicated. But you'll notice in all of this, I didn't really talk about neutrino mass, which I'll sort of briefly summarize. We know that neutrino mass is non-zero. We know that we have many observations of neutrino oscillations, and we describe these by 3 angles and potentially 3 phases in the form of the PM&S matrix. So here, this is the PDG parameterization. You have your 3 angles, theta 1, 2, theta 1, 3, theta 2, 3. And then here you have the Dirac CPU phase, if this is a Dirac neutrino mass. And then you have 2 relative Majorana phases. So you have potentially 3 phases. These would be 0. And what all this means is you have some flavor eigenstate for your neutrino mass. You use the PM&S matrix to then write it in terms of a linear combination of mass eigenstates. So why is this important? Well, dark matter and neutrino mass, I already talked about a few ways we think about dark matter. But none of these simplified models sort of incorporate a mechanism for neutrino mass, but these are some of our most compelling motivations experimentally for beyond the standard model physics. So there's a lot of motivations for beyond the standard model physics, sort of theoretical motivations. But our best experimental handles have so far been dark matter and neutrino mass, and particularly with the latest LHC results from at least HEPEC, where they hadn't found anything really, and the hint of the diphoton resonance went away. So the question is, can we make a model of dark matter and neutrino mass that explains the nature of dark matter? So we have some sort of dark matter model, like the ones I talked about. Also explains the nature and origin of neutrino mass, while also maintaining some of this relative simplicity that you have in these nice models, like the effective field theories with the simplified models. So, you're never supposed to ask a question if the answer is no, otherwise my talk would be over. So there is at least one way of doing this, that there may be others, but the way I'll talk about today is you add a scalar doublet, and you add some Majorana fermions, and they are going to be odd under some exactly conserved C2 symmetries, so they are dark matter. And they run through this loop, and you generate neutrino mass through this Feynman diagram here. So this is just a particular completion of the Weinberg operator where you generate neutrino mass. And you have some symmetry breaking here at the Majorana mass of these fermions here. And so this generates your neutrino masses at the one loop level, and these are often called Scoto for the Greek word of darkness, scotogenic, or Mall models, because it was proposed by Ernest Mall in 2006. And you get this loop diagram, or the loop will give you this mass term for the neutrinos. So this M sub R is the real component of this doublet scalar. The M sub I is the imaginary degree of freedom, and the N sub K are the masses of these fermions. And you have your Koplan constants.
So eta zeros, they don't pick up any vacuum expectation.
Exactly, yeah.
Because
So,
your Z2.
yeah, so it's like an inert doublet model.
Inert,
Yeah.
okay.
Except for now you have this interaction term here. So this minimal model has some nice features. You have a dark matter candidate, either the lightest of your Majorana fermions or the lightest of your scalar degrees of freedom. And it's also nice because the loop sort of gives you this quantitative explanation for why the neutrino mass is much lighter than the charged lepton mass without having to have tiny Euclides. And you can also have your new particles at the electroweak scale. So you can get realistic neutrino mass if you have sort of relatively large Euclides, while also having a particular particle on the order of 100 GeV. So that's not the only way you can get realistic neutrino mass in this loop mechanism, but the fact that you can now have particles at the electroweak scale is certainly appealing. Another advantage in this post-discovery of the standard model like Higgs, this model only has one Higgs particle, which will become important later. It's a very minimal extension to the standard model. You really only add this extra Majorana fermion and this doublet scalar. And because this is charged under the electroweak symmetry, you can also potentially have collider signatures where your collider signatures connect your dark matter, your mechanism of neutrino mass with your dark matter. So there's some issues with this. You can't explain the structure of the neutrino oscillation, that you can fit the angles for neutrino mixing, but you don't have a very good explanation for why certain angles may be a certain way, which I'll explain a little bit more later. And also, if you take into account, if you just take this naive equation here and you just take just all the parameter space without sort of ensembles about the structure of these constants here, and you take RGE equations, you take dark matter constraints, you take existing collider and precision like G-2, it turns out that it's severely constraining on this minimal model. So you have a lot of your parameter space, it would be significantly with that.
So for the collider, it's kind of a monojet. That would be your constraint.
So let me think here. So at least since these are charged under SU2, you'd get all the left constraints, and then you have like all these. So it would look like.
So what's the typical eta zero mass you need for your oscillation?
Let's see. So in this paper, they were looking. It was below TeV. So it was like like 100 GeV to about like 1 or 2 TeV, I think, where they looked for where they just did a scan of the mass for that.
So then let that lie.
No, but for a certain mass range, these would look. You might be able to see them on top of the like if you measure the W boson cross section. These would sort of look like that at the LHC. So you can get some constraints from that. But I'm not sure exactly what other constraints they looked at. Like you could get some like mono X.
Yeah, mono
X, yeah. Like a fat jet from a mono W, I think. And that might be, yeah, the mono jet, I think, the mono fat jet would probably be the best constraint. But I'm not quite sure. All right, so this sort of problems bring us to this idea of Plato's fire, where you use these non-abelian discrete symmetries. So we'll sort of discuss this. The name, at least, comes from the idea that, well, Plato thought there was 5 fundamental elements that made up all the universe, and one of them was fire, and that was represented by the tetrahedron. So this non-abelian discrete group is called A4. It's an alternating group of 4 elements, and it's the symmetry of a tetrahedron. So if I take all the rotations of this tetrahedron and label these indices, then all of the permutations of those indices will, the rotations that make this tetrahedron look like it's the same sort of object. But all those permutations will be the various permutations that this group A4 describes. So the nice thing is it has 3 distinct singlet representations. So unlike SU3 or SU2, you just have a trivial singlet representation. But this sort of behaves like a Z3, these singlet representations. But it also has these triplet representations. So you can get the 3 cross 3 to give you a singlets plus triplets. But the basic idea of this Plato's fire is that you create a mismatch between the charged leptons and the neutrinos. And you achieve this through using different representations of this discrete group. And this allows you to have large differences in the charged lepton mass while also generating non-trivial p-mass matrix. So specifically, the original proposal in 2001, they suppose that you take your Higgs doublet and now you make it an A4 triplet. So you actually have 3 copies of this Higgs field. You take the left-handed leptons and you organize them as a triplet under this A4, and then you have these right-handed charged leptons, and they have 3 different distinct representations. So this is at least why you can get a qualitative description of the different charged lepton masses, because they're different singlets. They get different Euclid couplings when you make an A4 invariant. And in fact, when you use this scheme, you're able to generate non-zero neutrino mass. You get a charged lepton mass matrix, which has this particular form where you have this matrix out in front. When you then diagonalize this, you get a residual Z3 symmetry in the charged electron sector, which is what this matrix is representing. See if you electron mass, muon mass, tau mass. And this leads to a neutrino mass matrix like this. So it's a very simple form. You have the diagonals as one value, the off diagonals as some other value. And this is exactly diagonalized by this matrix, which corresponds to what's called tri-bimaximal mixing. So it has this, if you look at this, you'll notice that it has 0 theta 1 3 entry, which is important. So this predicts an exact mixing matrix for the neutrino and mixing, and it's actually close, but it's not that close, because theta 1 3 is not only not 0, but it's not exactly small either. You know, and it's also really well measured, so like the deviation from 0 is pretty large experimentally in terms of the standard deviations. So in the original Plato's fire model, if you take this A4 and you break it to this residual Z3, but if you want to get this theta 1 3 not being 0, you have to break the A4 to a Z2 for the neutrinos, and then the A4 to a Z3 for the leptons. So you have to have this clashing symmetry, and whatever model you produce using these non-abelian discrete symmetries are going to have this sort of clashing symmetry between the charged leptons and the neutrinos. So what happens if we sort of add this to scotogenic models? We can actually accommodate what's called Cobi-Maximal mixing, which is a much more realistic form of neutrino mass mixing. So now you get theta 1 3 not being equal to 0. In fact, it's sort of allowed to vary, but the variance is proportional to theta 1 2. So it's a function of theta 1 2 and theta 2 3. So you have this nice correlation between the angles. You have a particular prediction for one of the other angles, and now you have a specific prediction for the CP violating phase. So you actually predict that it's maximal CP violation. And one way to implement this in the scotogenic model is in these diagrams here. So here you have this is different from the minimal model I showed earlier. This is a real scalar singlet under SU2. These are now fermion, vector-like fermions. This is the familiar Myron fermion. These are the standard model Higgs, here are your neutrinos. But you also now radiatively generate charged lepton mass.
So theta 1 3 not equals to 0. So that means you have chosen one of those A4 breaking up, A4 to Z3, A4 to Z2.
Yes.
So at what scale you are breaking these discrete symmetries?
So at least the way that Ernest Mah does these, he breaks it softly. So the absolute scale of the breaking, I don't think it's strictly fixed. But it's going to be on order of the size of the masses of these others. So I can explain it a bit later, but.
So don't you get into domain walls?
My understanding is since you're breaking it softly at the Lagrangian level that you don't have domain wall problems. But I could be wrong about that. So what happens is, well, if we look at this, these will carry some A4 symmetry or whatever symmetry you're using to do this. And then you'll break it here to generate a Z3 for your charged leptons. And then here you break the Z3 to a Z2 through an S1, S2 term here. So that's coming into your Lagrangian as like a M1, just like M squared S1, S2 term. So my understanding is since it's broken in the Lagrangian itself, you don't run into this domain wall problem. Since it's a dimension 2 term. But I haven't really thought about the domain wall issues very deeply. Yeah. But one issue this does have with this clashing symmetry, so as I said, you need this clashing symmetry. You have this S1, S2 term that breaks this neutrino loop. A4 goes to Z3, goes to Z2. But this now allows this term. So these X's are giving you your Z3 residual symmetry and your charge leptons. But now you have this S1, S2 term that breaks your Z3 to a Z2. So now you can generate a Z3 breaking term with these, but this is a very problematic diagram. You have to introduce Z3 breaking counter terms in order to make this finite. The residual symmetry scheme is then badly broken in this particular model. So this is also kind of a generically an issue in any model that uses this this diagram in order to generate your charged lepton masses, and this diagram to generate your neutrino masses. So if you use these sort of topologies for your diagrams, you sort of generically run into this issue. So another way to do this, instead of using a non-abelian discrete symmetry, you could have some Untitled interchange symmetry and get this Cobi maximal mixing. But you again have this issue where the symmetry, because you have these scalars and sort of both loops, you run into this issue again. So there is a solution to this proposed earlier this year. So if you just change these loops a bit, so now I changed my loop for my charged leptons. I'm back to that inert doublet from the minimal model. I now add SU2 singlet charged scalar. These are now Dirac instead of Majorana, and then the Majorana fermion is now this F here. And I allow the A4 to be sort of along this axis. So this is some A4 triplet. This would then be an A4 triplet. This is also an A4 triplet. And then this is an A4 triplet. And then everything up here is just A4 singlets.
So, but then mu E gamma, tau mu gamma, mu E gamma, tau mu gamma, those would come into play. Flavor violation indicates.
For these?
From the charge list.
Yes. So you can get. Let me think. Yeah, so you can, but the thing is, because you have this non-abelian discrete symmetry sort of at this issue, if you look at least for a lot of these models, if you look at this vertex and you have this is a triplet and this is a triplet, I think you get a suppression on at least some of the terms. But I think some people have looked into it generically, the case where you have a diagram like this and just looked at the various flavor changing mutual current contributions you get. And I don't think they're too problematic. That is, if you take these on sort of the order of like a few hundred GeV, and then you take this Cobi constant on the value you need to generate the correct masses.
Yeah, it
you're
depends
usually in
on
the right range.
the neutrino mass and correlating it with your flavor violation. So what so you are saying that it's consistent. You can find a consistent neutrino mass solution without violating flavor violation.
I'm saying that I think that they are consistent. So if you do this mechanism, so these particles now, in order for them to be sort of stabilized and make sure this doesn't get a fab, and you have all these issues, and you make sure that these are sort of dark particles running through the loop. You have these they're odd under an exactly conserved Z2. So I just call this the dark Z2 or dark parity, just for this talk. And then these particles then carry some new gauge charge, so some dark gauge charge. So now you're able to establish these clashing symmetries, because when you break the Z3 to a Z2 with the S1, S2 term, it will introduce corrections to the mass here, but they'll occur at loop 2 order, and they'll be finite. So the corrections to this residual Z3 matrix will be very small. And they're also not arbitrary anymore. So this is good. So you can save this Cobi maximal mixing. But the downside is that you've now significantly expanded your particle content compared to the most minimal possible model of the scogenic models. So here's my standard model particles. You see that now they're charged under this A4. They're even under this Z2. There's this extra flavor Z2, and that's just to prevent trio level charged lepton mass. But it's softly broken by It's exactly conserved except for some softly breaking terms in the scalar sector. You have these new fermions, so you have this A4 triplet, which is a direct fermion. It carries this new dark charge. You now have a vector-like fermion. It's an A4 singlet. It's odd under, this Z2. You have this Majorana fermion. It is also odd under Z2. And then you have some new scalars. You have that inert doublet, carries dark charge. You have this extra singlet scalar, carries dark charge. And then you have this real scalar, which carries Z2 parity and is a A4 triplet. And you see that this chi also has this flavor Z2, but it's exactly conserved in all but one term. So we've expanded our particle content, but one nice thing we get is that since this has now two stabilizing dark matter symmetries, you can potentially have multiple components of cosmological dark matter. So it's a sort of bonus. So that's sort of our introduction now to my binary tetrahedral scotogenic model. So I'll talk a bit about it. The motivation is, if we look at A4, there's an alternative you can use, which is called the binary tetrahedral group, also known as T prime. And it has the same multiplication rules as A4, so that 3 by 3 rule, and it has the same non-trivial singlets, but it also has these doublet representations. So it's a double cover of A4. So it has now 3 distinct doublet representations with these multiplication rules. So you can, if you multiply one of these doublets by a triplet, you get a doublet back. You also have this sort of SU2-like multiplication rule as well. And the nice thing is that this T prime group has been used previously to predict the Cobi angle in one of these non-abelian discrete models. So this is good. So you'll notice that I didn't really talk about CKM mixing when I was talking about the Plato's fire model, and that's because in that model, you sort of just have trivial quark mixing. So at least you maybe, if you can't predict the full CKM, the largest angle is the Cobi angle. So if you can predict this Cobi angle, you're well on the way to having a much more realistic CKM mixing matrix in one of these flavor models. So another important thing to note is that any model that uses A4 could just as easily use this T prime, since the singlets and the triplets under these two groups behave in the exact same way. Like it's not really sensible to distinguish them unless you have these doublets. So just to briefly talk about how Frampton produced the Cobi angle. You take your left-handed doublets. So these are SU2 doublets separately, and you combine them into one large T prime doublet. So you have your first 2 generations, your charm and your strange, and your up and your down. These are both SU2 doublets. This is the first component of the T prime doublet. This is the second component. Then you take your right hand charmed-like quarks, make them as a different doublet, and then your strange in yet another doublet. Frampton also had this case where he took the Higgs and he made it a triplet under T prime. So basically, where this Cobi angle is coming from is, ostensibly, it's coming from the mismatch of these T prime representations. Because you have these different T prime doublets and you have this triplet and this Higgs, you're able to generate a mismatch between the up and the down sectors, and that's where you get the non-trivial CKM. You get a Cobi angle that's not quite the correct angle, but it's pretty close, and it's much closer than predicting trivial coordinates. So the idea is, can we take this in a scotogenic model, have the Higgs as a singlet, and generate Cobi maximal neutrino oscillation, and also get this non-trivial quark mixing. So if we just take the same particle content as the previous A model and take our standard model quarks, give them that same assignment as Frampton, change the charge to be analogous to some other case. But then if you add vector-like fermions and some extra scalars, it turns out that you can actually generate the quark mass. So these particles, these are uplike, they're vector-like fermions. They're now a doublet under T prime. They also carry dark charge and this dark parity. And then there's these particles here. They're added because, if you'll notice, I've allowed right-handed first two generations to carry charge under this additional U1. So now you have to cancel anomalies, and so these have they're now chiral under this U1 in order to cancel this anomalies, but they're otherwise vector-like under the standard model. And then you add an additional scalar doublet and an additional scalar singlet, but now they have charge and parity. And then you add these two particles to break this U1 to a residual Z2. And the reason you really want to do this is because now that you've given charge to these first two generations of right-handed quarks, you have this new gauge boson that's coupling to your quarks. And so you really want it to be massive in order to escape various constraints. So you want to give it a mass, and these two particles will couple to your gauge boson and do that through Higgs mechanism. The top, it's actually really hard to generate a radiative mass and get the right values. So the top and the bottom still receive their masses at tree level from the standard model Higgs. So here's the one loop diagram. The lepton mixing is the same as A4 as I mentioned. And these new particles in G prime yield this one loop quark mass. So here you have that zeta 1. It has one charge. It has integer charge under this U1. So all the particles with half integers will be, when the U1 breaks, they'll be like odd under some residual parity. Whereas anything even will be, won't be stabilized by the extra U1. So you have these scalars here that are, this will get a VEV, this will also get a VEV, and you'll generate the non-zero quark mass. And then here you have the vector-like quarks that are the up-like and the down-like. And they have a mass that softly breaks this T prime symmetry to a residual Z4 symmetry. So when you do this, you can generate the first two generation of quark masses. You get this expression for the quark masses. So you have your coupling for your left and your right hand quark. You have some mixing angles here between your rho and your sigma. You have your loop factor, and then you have this 2x2 matrix, and it depends particularly on the T prime assignment and these like loop functions, right? So these are just logs of ratios of masses of the scalar degrees of freedom and your vector like. So this mass matrix here will depend on these mixing angles, the VEV of the standard model Higgs, and it will also depend on the mass matrix of the vector-like quarks. So the CKM is coming again from the mismatch of the T prime assignments in the up-like and down-like sector, and it depends on the vector-like quark mass matrix, which in a particular basis you can write as this. And the reason why you want to write it like this is if this was an exactly conserving T prime mass matrix, the off diagonals would be 0. And then this M13 term would also go to 0. So for this to be only, like, for these off diagonal elements to just sort of not have a large correction to the T prime and break it to a Z4, these elements are going to be smaller than this term here. So this is a particular basis. And then when you do this, the CKM angle can be extracted. So you get some value for your up-like sector, some value for your down-like sector, and you get a Cobi angle that's proportional just to the ratio of this delta to this M13 term. And there's some restrictions. These two should be small because we want this to be sort of qualitatively. We want the ratio of the diagonal elements over the off-diagonal elements to make the off-diagonal elements proportionally smaller. And then there's some restriction here just from the particular basis I used. But the end result is, if I now plot my physical, or my predicted Cobi angle in degrees versus this delta over M13 term, you get this value. So this band here is the actual physical Cobi angle. So you see that you're only really exactly at that center when you're very close to this, where the ratio of these are exactly equal. So if you might be very close to 1 and be able to get the exact Cabibbo angle. But even if you stay within 30% of the Cabibbo angle, you have a fairly large range in these two parameters. And so this is able to yield a more realistic Cabibbo angle compared to the A-form model, which predicts 0. And it does so as long as T prime is broken. So this is going to be non-zero as long as this T prime symmetry is broken by the vector-like quark masses. And another point to bring up, though, is that if I'm within 30% of the physical Cabibbo angle, then if I look at the deviation from the Cabibbo angle and then all the rest of the CKM, like the next largest CKM angle. So my prediction in this model is 0 for the next largest CKM, at least at this level. And if I look at a deviation between the physical Cabibbo angle and the prediction at this 30% level, that deviation is about the size of the next largest CKM mixing element. So it's sort of always suggestive of maybe making a mechanism whereby this deviation from this mixing angle to the physical Cabibbo angle is proportional to the next order of your Cabibbo. So right, if I take the Cabibbo angle on this deviation of 30%, that's about the size of the next largest CKM angle. So it's important to talk about how this extra gauge symmetry is broken to Z2. Both this zeta 1 and zeta 2, this is singly charged under the additional gauge, this is doubly charged. They're both able to receive vacuum expectation values. And in order to make sure that our Higgs field ends up to be mostly like a standard model, the VEVs of these two particles are taken to be much larger than the standard model VEV. And if you do this, you get a contribution from after the minimization equations and the constraint equations to the Higgs mass, so it deviates from the standard model value. But so in this particular normalization of the VEV, this is just the normal standard model Higgs mass. And so you see there are some corrections, but these can be argued to be small, given the particular of these quartic couplings and some of these ratios. Another important part, though, is that the particles that cancel the anomalies generated by giving the right-handed quarks charge under this U1, in order to generate a mass, you need this doubly charged scalar singlet to receive a VEV, and it should be on order of TeV to make these. These are colored particles. So you don't want to be producing these colored particles that are massless. And so you want to escape all vector-like quark bounds. If this is on order of a TeV, then the masses of these top-like and bottom-like anomaly canceling vector-like quarks should be fairly large, and then you can sort of justify this VEV being large through this other observation. This also generates a non-zero mass for the Z prime given here. So since the C prime couples to the quarks, we again want it to be fairly heavy. So you can, all these three assumptions sort of work together. You want to assume that this VEV is much larger than the Higgs field VEV so that you can get a mostly standard model-like mass and couplings, but then you also want to generate a fairly large C prime mass from existing constraints, and also you want to make these relatively heavy. And again, this phi is, the nice thing about this is unlike the Frampton model, this Higgs is now a T prime singlet in this photogenic model. So you're not predicting a bunch of extra degrees of freedom for the scalar doublets. So there's also some important constraints. This is from ICHEP Atlas results. Should be updating them relatively soon. This is a search for elliptophobic Z prime, which, if you'll notice, the Z prime in this model, it doesn't couple to any of the leptons. All it couples to is quarks. So you see that there's this gap in their latest search results at this 1 to 2 TeV window. And then if we also, wrong way. If we also take into account the ATV results, because they did look at this window, but do it in a simplified model, because we do have some dark matter, and they are looking for some mono-X signature, this would be relevant for a model like this. You can see that there's this window here between, on the order of a few hundred. These are in TeV for the dark matter mass, so if you're in a few hundred GeV for your dark matter, and sort of in a 1 to 1.5 TeV range for your Z prime. Even these A prime searches, there's some gaps as well. So if you take this Z prime on order of around TeV, you should be able to escape existing LHC constraints. And then you also are able to avoid some of the largest constraints on Z prime searches because it's lobophobic from MikeLab. There are also flavor changing neutral currents that you might need to care about, but for all the new particles, they're severely restricted. They either have some residual Z4 symmetry if it's in the quark sector, or it respects this U1D. And there are a lot of terms that don't break T prime at all at the Lagrangian level. So it's only in the quark lepton sector, it's only broken by this S1, S2 term and fermion masses. So the scalar terms in all will generically respect the full T prime, or there is some residual symmetry from the neutrino sector, quark sector, or charged lepton sector. But they can still contribute, since you have all these new charged particles running through these loops, they can contribute to like KK bar mixing, which you can estimate the Wilson coefficient at. You'll get an expression like this. But this mass splitting is the mass splitting between the charged scalars. So this is going to be small for other reasons on order of GeV. So this whole thing is below experimental bounds, at least at this estimate. So at least at the leading order, KK bar mixing and all these other flavor changing neutral currents are not a problem. And now on to the dark sector. So there are automatically two dark matter candidates in this model. You have your lightest particle in your Z2 stabilized sector. You have this your vector-like fermions, this Myron fermion, or so some fermionic particle, or the light, if the scalar is lightest, the lightest one of those. You also have the lightest one in the U1 stabilized particles. So again, you have some scalar degree of freedom, and then fermion degree of freedom. And you also have a bunch of Z prime interactions. And beyond this, you have a lot of standard model dark matter interaction terms. So here you just have a generic Higgs portal. These are two Higgs fields, and then you have your two scalars. So no matter which scalar you have, you'll always get a term like this. So when the Higgs gets a VEV, you'll be able to have many sorts of interactions you can get. Right? This is your typical Higgs portal. You also have this sort of structure here where you have charged leptons coupling to this N, this U1 neutral fermion, and then one of the charged scalar degrees of freedom. And then also they can couple to neutrinos. Here, the flavor of this lepton is going to correlate to the flavor of this N, due to the T prime symmetry. So, for instance, if I look at the coupling to the electron, and then this will couple to the electron N1, muon, N2, tau, N3. So depending on which one I choose as my dark matter, N1, N2, and 3, those are all sort of labels, and they'll be related to the neutrino oscillation in some way. But the labels are sort of arbitrary, right? I could have some like inverted hierarchy. So maybe this N3 is actually my lightest. And in that case, it would couple to the tau instead of the electron. But these labels are correlated from the T prime symmetry. So the flavor structure is fixed by the non-abelian discrete group. You get into a similar sort of case here for the right-handed fermions. And then you also have a similar sort of correlation between the real scalar charged leptons and the vector-like fermions. So let's say this neutral vector-like fermion is the lightest. Then you get sort of interesting case where the mass of the mediators here would be what is determined here. Anyway, so X and Y are the mass eigenstates of this eta, chi, and phi sigma mixing. And in addition to these interesting dark matter standard model interactions, there are also some noteworthy dark matter interaction terms. So you get a scalar fermion interaction. So you have one of this is the rho sigma eigenvalues. So the rho and the sigma will couple to this N,
and this vector light fermion. So you'll notice the rho and the sigma, they carry both dark charge and dark parity. The n's only carry dark charge. The e's only carry dark parity. So now you have this interaction here that sort of mediates the communication between these two sectors. So depending on your masses, this can actually, this might be able to, well, anyway, I won't talk about that. But this complicates things quite a bit. And then you also have the scalar interaction term you can write down that's invariant under everything you can think of in the theory. So you have this rho, eta, s, and this zeta 1. So again, you have this rho, it has dark charge, dark parity. Eta has just dark charge. And s has just dark parity. So these two terms allow sort of mediation between the Z2 stabilized and the U1 stabilized dark sectors. So even though I have these two dark sectors, I'm able to have some sort of communication between them through these additional interactions. So these scalar interactions, they actually add quite a bit of additional complications because it allows that my rho and my s could annihilate into zeta and eta, or my eta could decay depending on the values of some of these things. So suppose rho isn't my dark matter, but has some relatively long lifetime, right? If I find some way to generate a relatively long lifetime, then my dark matter's history can be much more complicated. As my various dark particles could decay to, it would be like a semi-annihilation case, or you could have semi-annihilation where you have two dark matter particles and they annihilate to one standard matter particle and then one dark matter particle. Or you could also have one of your species of this dark matter that is just relatively long-lived being produced early in the universe and then decaying pretty significantly throughout the lifetime. So this can potentially significantly change your history of your dark matter. Another thing is if these masses are close, these scalar masses, then and I prevent this rho from decaying to these fermions. So if I go back, look at this fermion thing. If I sort of kinematically forbid this by just having these two masses be similar or in the same order, then this rho could potentially be like a third stable species. So even though you only have two stabilizing symmetries, this extra particle it's not really going to decay to the others, and the others won't really decay to it because these terms are small. That's something I didn't really look into in much detail because I just wanted to see if this model could produce realistic dark matter at all before you make it much more complicated. So even if we choose the masses and the coupling constants to get rid of these terms and focus on the case of a simple two-component dark matter model, what happens? So I took just the fermion, the lightest neutral fermion n, and the lightest real scalar s as dark matter. And then now you have a bunch of mediators. All the other particles can be thought of as mediators, and you have a very complicated mediator structure. But you've eliminated some of these potentially interesting cases.
And so all these dark matter candidate masses are of the order of weak scale or something.
Yes. Yeah.
So all of them are kind of colder.
Yeah. Well, so I think you could maybe, in this, when I looked at it, they could all be called dark matter, but it turns out that if you look at, if you just sort of ignore the fact that you'd have fine tuning, you can make this S very small, like on the order of MeV, and then the N on order of 100 GeV, and you're actually able to fit both the relic density and sort of evade the Lux 2016 constraints. But then the problem is because this S couples to your fermions, and you have a fine-tuning problem with making it so light. You have to have like coupling constants, and it's an exact right way to get it that light. But you have problems with direct detection because it couples directly to fermions. But it turns out you can actually at least meet the relic density with having one of these dark matter species. If that's all if the direct detection and thermal relic were all you cared about, you can actually make like a subdominant component to be very, very light, like on order of hundreds of MeV, which I thought was interesting, but then it's sort of ruled out automatically by direct detection.
But you have-
Sorry, indirect detection.
So
not
you
direct
have three species, so you satisfy the relic abundance including at least two of them, because even if the other one is small, so that means your relic abundance is not necessarily coming from one.
Yeah, so in that case, actually, I was only looking at the case where I had assumed that there were only two species.
Two species.
But even in that case, you can get a subdominant component that's fairly light. But again, indirect detection constraints sort of rule that out. So even if we make these bland choices, though, you have very rich dark sector. So you have, I can't really read it. These are the ends. They can decay to long charge leptons and neutrinos. They can also annihilate into Z primes, depending on the mass of the Z prime. You could have like this was sort of looked at a simplified model with the dark Higgs. What happens if you get the thermal relic by decaying to the Z prime instead? And then, of course, you have the Z prime mediation to the first two generations of red chain quarks. The S kind of do this G channel with the vector-like fermion to the leptons. And then, of course, you have this scalar portal for the S. So it can couple to all the scalars of this quartic term.
So it annihilates into Z prime. So your N must be quite heavy. Z prime is your heavy, like you said, like an order of 2 years.
Yes. So if this diagram is not going to really be allowed if the Z prime is right. If this is kinematically forbidden, but if you don't take into account the Z prime constraints, and like you could potentially have this diagram, right? Like if you had a very small coupling constant, you could maybe evade the collider constraints, and then you could have this diagram, but then again, the coupling constant is small, so it doesn't really help you for the thermal relic, but it's still sort of interest. Just to throw it there as possible, naively, I guess. So to sort of more concretely explore the dark matter in the model, I picked a concrete set of masses. So basically, here's all the masses I picked. But the important parts are the mass of this N had to be less than 245 GeV to be the lightest in its sector. The scalar had to be less than 450 GeV to be the lightest in its sector. But these masses, this wasn't a scan. This was just like, well, I'm going to choose masses for these scalars to try and avoid constraints that I know about on these sort of charged scalars, and then make a realistic spectrum. Choose a coupling constant for the dark sector of 0.1 and a mass of 1.2 TeV for the Z prime. So this sort of eliminates a lot of the interesting diagrams. You basically have annihilation to electrons and neutrinos for your scalar dark matter species, and then electrons, neutrinos, and quarks for your fermionic dark matter species. And then when you do this and do a scan over in parameter space, the colors aren't amazing for this vector, but there's this light yellow region you can sort of make out here. That's just areas where you meet the relic density. There's this light blue area, these are points in this MS-MN plane. So this is the mass of the fermion, this is the mass of the scalar, and GeV. These points here meet the Lux 2016 and Panda X direct detection results, so they're not ruled out by those two experiments. And then this red region is the region that it really matters, because this is the region where you're able to predict thermal dark matter, and you are not ruled out by direct detection constraints. So you see there's actually quite a bit of space left here. You're in the 100 to 200 GeV range for both species. Also, at various points in here, you'll have various different ratios. So in some of these parameter space points, you'll have cases where one of the dark matter species is on order of a few percent. So it's, as far as most people are concerned, it's negligible. But then in a lot of this space, you have like close to 50-50 with the thermal dark matter. So you have these two species. Went back, not forward. So in addition to the dark matter phenomenology, these vector-like quarks, I call them vector-like even though they're chiral under this U1, because I don't really know what else to call them. It doesn't sound weird. But this top like and bottom like quark, they have some interesting signatures at the Large Hadron Collider. So that they're colored, so they can be produced, pair produced, just like quarks can through gluons. But then because of the structure of the theory and their choices in U1 charge and all the flavor symmetry, they'll decay to, this top like one will decay to a bottom like quark. And then depending on my assumptions about dark matter, it'll go to an electron plus missing energy. And then the bottom like will go to a top, an electron and missing energy. And so this again is coming from the assumption that this N1 is dark matter. But another possible decay chain is if N2 or N3, if they are stable in the lifetime of the detector, you could get different correlations with your flavor. So you could get a muon and missing energy, a tau and missing energy. So it does depend a bit on the details of the model. And the lifetime of the other species of this A4 triplet, T prime triplet. Anyway, so these sort of decays are similar to SUSY and vector-like quark searches, but these particles will only decay through that channel. So this is really the only way to look through them. This is like the best way to look for them. They're not going to decay through other ways. So if you look at some SQUARK searches where they couple to the third generation of quark, you can find decay searches where they'll have a lepton and this flavor. So the flavor is going to be correlated to the particular SUSY model and the SUSY structure. In this case, that's not the case. You also might have different angular variables since you now have a fermion instead of a SQUARK. And then, of course, you can't search for these with a dijet plus missing energy or W decays or for the case of vector vectors. So these are things you could get bounds on from looking at SUSY searches. You could definitely use existing SUSY searches to put bounds on them, but you can't use all the SUSY searches. And for instance, some of the worst constraints on SQUARKs are coming from dijet plus missing energy that push up the mass up to like 4 TeV now, I think. So you can avoid that constraint at least with these sorts of particles, even though you have a similar sort of decay. All right, so just a summary of this model I've talked about today. I've demonstrated it's possible to generate a non-trivial CKM mixing and a realistic P-S matrix in one of these scotogenic models. That means I'm generating the masses of my quarks, leptons, and neutrinos through one loop order, where all the particles running through the loop are part of the dark sector. And I've done so using this T prime symmetry. I've shown how the extension to the quark sector allows new dark matter standard model interactions, where now I have vector-like quarks instead of colored scalars, which is typical for a lot of models, such as SUSY. And this adds some interesting Z prime interactions because now you have a leptophobic Z prime, which is sort of interesting, I think. And I've shown how it's able to yield a viable two-component dark matter model. So this can produce points in the parameter space where you have two components to cosmological dark matter, and you are able to meet all the constraints I was able to think of. And there's a bunch of new particles, and so they have potentially many interesting signatures at colliders. So just broadly, conclusions and future discussions. Hopefully I've impressed upon you how these scotogenic models provide an interesting framework for both neutrino mass model building and dark matter model building, as well as some interesting collider signatures, sort of as an aside. Hopefully I've demonstrated and talked a bit about how non-abelian discrete symmetries, particularly this T prime symmetry, are of continued interest in model building. And even though I looked at blind assumptions for dark matter, this binary tetrahedral model has potential for much richer dark interactions. So keep going back and so forth. Thank you very much for your time and attention.